Hello, everyone. Welcome to the fourth webinar for year 13. Today's topic is matrices and mappings. So I hope you enjoyed the first assignment on maths. Now this is the second one. You might know about matrices. You've studied something. A matrix uh, in a matrix can represent a linear transformation. And the definition of a linear transformation is given to you in the assignment. Um, and yeah, so the first problem, this is a linear transformation. Well, let's just take the definition of a linear transformation from assignment just to so we understand what we're talking about. Right. So a linear transformation. It looks like this. So it transforms a vector into a combination of can transform a vector into another vector. Okay. Transforms a vector into another vector. And it is done via a matrix. And one of the properties of a linear transformation is that for the vector 0, 0, 0, 0, as you can see, will always be transformed because it's 0, 0, etc., 0 into vector 0, 0, 0, 0, 0, etc. So the 0 vector is always its own image. So if you take a rotation, for example, rotation about the point 0, 0, then under that rotation, the point 0, 0 always is mapped onto 0, 0. That means, so a rotation is a linear transformation. But if the rotation is about a different point, then no, it's not a linear transformation because 0, 0 does not 0, 0 does not go into 0, 0. For example, rotation about I don't know, 2, 2. Yeah, so not linear. Whereas a rotation about point 0, 0 is linear, as you can see, 0, 0 turns into 0, 0. So it is linear. Okay, that's not the definition of linear. It's not that if 0, 0 is turned to 0, 0, it's a linear transformation. No. It's a linear transformation if it can be written like this. Yeah. All right. So in a basketball league, teams earn 2 points for a win, 1 point for a draw, and 0 points for a loss. I don't know if that is true. Maybe. Never had any interest in basketball. But yeah, so this simply means that a 3-dimensional vector is mapped onto a 2-dimensional vector. The vector that we're talking about is the vector consisting of the number of wins, the number of draws, and the number of losses, whereas this is the number is a 2-dimensional vector with the top number representing the number of games played, and the bottom is the number of points won. So I'm going to use, we need to find a matrix of this transformation. Well, to do this, we need to construct a system of equations. So for example, how do we get the number of games played if we know how many wins, how many draws, how many losses? Well, it's quite simple. W plus D plus L equals to G. Right? So if you add the wins, draws, and losses, you get the number of games played. If you want to know the number of points earned, Well, you know that you earn 2 points for each win, plus 1 point for each draw, and 0 point for each loss. And this is the system of equations which can be turned into matrix form like this. 1, 1, 1, 2, 1, 0, multiplied and multiplied by the WDL, and that is equal to number of games and the number of points. This is the matrix equation. These are equivalent. These equations, this system of equations is equivalent to this matrix equation. And this is the matrix of the matrix T. So the matrix T hat is 1, 1, 1, 1, 1, 1, 1, 2, 1, 0. Okay, let's check if that actually makes any sense. So check. Imagine that we have a team which played, which had a team has 3 wins, 2 draws, and 2 losses. That means that the vector of the games is 3, 2, 2. So we get 1, 1, 1, 2, 1, 0. We multiply this by 3, 2, 2. And that becomes 1 times 3, 1 times 2, and 1 times 2. So that's 3 plus 2 plus 2. And on the bottom, we have 2 times 3, so 6 plus 2 plus 0. And that is 7 and 8. So what does this result mean? That 7 games and 8 points. Is that true? Well, let's have a look. The team had 3, 2, 2, so 7 games. The team played 7 games and they earned 2, 6, and 2, so 8 points. In the chat, can you let me know, are you familiar how to multiply matrices? Do you know how to multiply matrices? Ah, lovely. Okay, so you know what I'm talking about. So B, that's the more interesting question. Is T 1 to 1? 1 to 1. What does that mean? Well, it means that if one vector if one vector is mapped onto one vector, basically, could we have 2 different vectors creating the same image? And yes, so let's see. There's the trivial case. So trivial case, if you have 0, 0, 0 is mapped, if you played 0 games, 0, if you had 0, 0 wins. Ooh. Just realized something. Okay, in the in the context of this problem, if you had 0 games, 0 0 wins, 0 draws, and 0 losses, you played 0 games and you scored 0 points. However, if you played, let's say, if you scored 1 win, minus 2 draws and you had 1 loss. Okay, that doesn't make any sense. Mathematically, we're talking about the matrix, right? So 1 minus 2, 1 will be mapped also on 0, 0. You can test that. Let's test that. 1, 1, 1, 2, 1, 0 multiplied by 1 minus 2, 1. So the top is definitely 0, and the bottom is 2 minus 2, also 0. But also 1, 1, 1, 2, 1, 0 multiplied by 0, 0, 0 is also 0, 0. So the same image has two for 2 different inputs you have the same output, and that means it's not a one-to-one, not a one-to-one. Now, if you're saying, but you can't have a negative number of games, true. Let's see if we can invent something with a positive. So, for example, you have 1 win, 1 draw. Nope. 1 win, 0 draws, and 2 losses. That's 3 games and 2 points. Or you had 0 wins, 2 draws and 1 loss. That means you played 3 games in total and you scored 2 points. So you have two different vectors with the same image. So no, not 1-to-1. Okay, does that make sense? Okay, lovely. Problem 2, which of the following transformation is in the 2D plane are linear, and find their matrix if they are linear. So a reflection in the x-axis. So reflection in the x-axis, it is a linear transformation, and if we have the x-axis, y, so this vector and this vector, so vector 1, 1, 0 turns into 1, 0, and vector 0, 1 turns into 0, minus 1. So the matrix is 1, 0, 0, minus 1. Yeah, that's a reflection in the x-axis. It is linear. B. A rotation 270 degrees about the origin. So you have y, you have this vector and this vector. And now this is vector I, this is vector j, and they become, after 270, I and j. Yes. So I turns into 0, minus 1, and j turns into 1, 0. So the matrix is 0, minus 1, 1, 0. So to find the matrix of the transformation, we simply write down what the base vectors turn into. So I vector 1, 0 becomes 0, minus 1. So the first column is 0, minus 1. And then this is 1, 0. So if you make, so these are the images of I and j. Images of I and j, of the base vectors. C. Translation by the vector. Well, translation is not a linear transformation, not linear, because, well, 0, 0 is not transformed onto 0, 0. So that's not a linear transformation. C, D, a shear parallel to the x-axis. A shear, so a shear works the following way. X turns to x plus y. So this vector doesn't share parallel to the x-axis. Oh yeah, y doesn't change. The x changes. Yes. Right. Yes. So now let's see. Let's see what the image is. So 1, 0 becomes 1, 0 because y is 0. And 0, 1 becomes 1, 1. Okay, so the matrix is 1, 0, 1, 1. That is a share. And it is linear. Okay. E projection onto the y-axis. So you have a vector, and the image is the projection. So it simply means that the x coordinate is transformed onto 0, and the y coordinate is transformed onto the y coordinate. Oh, it does look like a linear transformation. Let me just yeah. So the matrix, so vector 1, 0 is transformed onto 0, 0. Vector 0, 1 is transformed onto vector 0, 1. So the matrix is going to be 0, 0, 0, 1. And it is a linear transformation. However, it's a singular matrix. All right, nice. Have rotation about 180 degrees about the point 2, 1. So it's not linear because 0, 0 is not mapped onto 0, 0. That's quite straightforward. An enlargement to scale factor 1/2 centered at the origin. So G enlargement. So if you have a pair of vectors, enlargement scale factor 1/2, so the vectors become smaller. So the matrix is 1/2, 0, 0, 1/2. So it is linear. And F, an enlargement scale factor 3 centered at the point 0, 1. So that's not linear because, well, you can imagine that 0, 0 does not turn into 0, 0 because the center of enlargement is at the point 1, 0. So I hope that makes sense. So this is just a practice question. So problem 3 is a practice on matrices. So the transposed matrix, so AT would be 1, 0, minus 1, 3, 2, 1. So to get the transposed matrix, you just switch the rows and columns, and then now we need to find ATA. So that becomes 1, 0, minus 1, 3, 2, 1 multiplied by A, which is 1 minus 1, 2, 0, 3, 1. And you can, so that's 1, minus 1, 2, minus 1, 10, 1, and then 2 minus 2 plus 3, 1, and 4 plus 1, 5. So it's a 3 by 3 matrix. So this is a 3 by 2. This is a 2 by 3. So this is a 3 by 3. It has to be. And B, now the other way around. Now, multiplication of matrices is non-commutative. That means that AB is not BA. And I will demonstrate that. So AT times A is not the same as A times AT. So 1 minus 1, 2, 0, 3, 1, multiplied by 1, 0, minus 1, 3, 2, 1. So this is a 2 by 3, and this is a 3 by 2. So we cross out the 3. So the answer is going to be a 2 by 2. So the first one is 1 plus 1, 2 plus 4, 6. Minus 3 plus 2 minus 1. Minus 3 plus 2 minus 1. 9 plus 1, 10. So that is there. So clearly they're different. They're even matrices of different size, right? So yes, matrices. Inverses. Now here, I might bring something new to the table. So if you've studied matrices at school, hopefully I will be able to show you something new. Now, find the inverse of a matrix. Now, you know how to find the inverse of a matrix using the formula. I tend not to use the formula. I really don't like it. I mean, for a 2 by 2 matrix, you would obviously use the formula. You don't need anything else. But I'll show you a different method. It can look complicated, but for bigger matrices, it's actually simple. Okay. So what do we do to find an inverse? To find an inverse. This is called I mentioned that I was a YouTuber, and I actually had a video on this. And I forgot the name of the method, but Gauss-Jordan. Yes, Gauss-Jordan method. Gauss-Jordan method. You write the matrix, so 3, 2, 4, 3. Then you write a vertical line, and then you draw the identity matrix next to it. And then you transform, you do operations on the lines of the matrices such that to obtain an identity matrix on the left. So for example, here, I'm going to subtract line 1, subtract line 1 from line 2. And we get 1, 1. On here, we get minus 1, 1. Line 1 doesn't change, so 3, 2, 1, 0. So I've simplified the bottom part. Now I subtract, so we do the line 1 minus 2 times line 2. Right, so we do this minus double this. So this becomes 1, 0. So 1 plus 2, so that's 3. And then 0 minus 2, so minus 2. And the bottom line doesn't change. So 1, 1, minus 1, 1. And then we do line 2 minus line 1. Minus line 1. And you can see that this becomes 0, 1. And then minus 1 minus 3, so minus 4. and 1 plus 2, 3. And here we have 1, 0, 3 minus 2. And the matrix that we have here is the inverse. So we started from this matrix. This is matrix A, and this is matrix A minus 1, the inverse. So for a 2 by 2 matrix, it is certainly an overkill. But when you're dealing with a 4 by 4 or a 5 by 5, I find that this method is faster. It's faster and it's really satisfying. Let's check. Let's test. Um, test. 2, 4, 3 multiplied by 3 minus 2 minus 4, 3. So multiply, so 9 minus 8, that's 1. Minus 6 plus 6, 0. 12 minus 12, 0. And minus 8 plus 9, 1. Ta-da, works. Okay. Now, yep, do you like the method? Do you understand it? I'll show it again, don't worry. If you, right. Okay. Now, problem 5, I'm going to solve this problem using the same method, Gauss-Jordan method. So here I have a system. Well, yes, you've done these in year 8, right? Of course. What am I doing here? I'm giving you a simultaneous equations and saying solve the simultaneous equations. Obviously, I want to demonstrate the method here. So this equation can be written as matrix multiplied by the vector x, and that's equal to vector b. What do I mean by that? Well, the matrix is 2, 3, 4, minus 1 multiplied by xy, and that's equal to 7, 5. Okay. Well, you can check that this is in fact true. If you start multiplying out, you get 2x plus 3y, 4x minus y, and that's equal to 7, 5, which is just equivalent to what we have here. So I'll delete that. But we know that if this is true, then we can write that the vector x is a minus. Oh, let's do it properly. So a multiplied by vector x equals vector b. So I'm going to multiply both sides by a minus 1 on the left. Because we know, remember, the matrix multiplication is not commutative, so you're multiplying it on the left. So a minus 1a multiplied by x equals a minus 1b. And then this is the identity matrix, so it's simply x is the inverse matrix multiplied by vector b. So to find x and y, we simply need to multiply the inverse of this matrix by 7, 5. So let's find the inverse using Gauss-Jordan method. Using Gauss-Jordan. So 2, 3, 4, minus 1, 1, 0, 0, 1. So first I do, let's do line 2 minus double line 1. So line 2 minus 2 times line 1. And that becomes 0. 1 minus 6, so minus 7. Minus 2, 1. 2, 3, 1, 0. Okay, so then I divide line 2 by -7. Divide line 2 by -7. So that becomes 0, 1, 2/7, -1/7. So 2, 3, 1, 0. And then subtract. You do line 1 minus 3 times that. So that becomes 2, 0. 1 minus 6/7, so that's 1/7. 0 plus 6/7 plus 3/7. 0 plus 3/7, so 3/7. And 0, 1. 2/7 minus 1/7. And then you divide the top by 2. Divide by 2. So you get 1, 0, 1/14, 3/14, 0, 1, 2/7 minus 1/7. So the inverse matrix is that. So xy is 1/14, 3/14, 2/7 minus 1/7 multiplied by 7/5, and we get something. We get, well, it's not fantastic. So let's take 1/14 out, and it becomes 1, 3, 4 minus 2 times 7, 5. So 1/14, open bracket, 7 minus 15 minus 8, 28 minus 10, 18. And so that's minus 4/7 and 9/7. So that's the answer. I'm not sure I haven't made a mistake, but let me double check. One, so 2, 3, 7, 4 minus 1, 5, 11/7, 9/7. E. Y is correct. X is not. Of course. 7 plus 15, 7 plus 15, 22. 22. So that's 11/7. Okay. Well, not a huge mistake. I was a tiny bit off. Nice. So yeah, that's how you can solve. That's how we can find x and y. Yes. So xy is the inverse of the matrix multiplied by 7, 5, and that's 11/7 and 9/7. So yeah, we have a very convoluted way of doing a very simple thing. However, it starts to make a little more sense when you talk about a 3x3. Well, of course, of course, 3x3 matrices can be solved easily. So we have matrix A multiplied by x, y, z, and that's equal to 3, 9, 10. And that means that x, y, z can be written as the inverse of A multiplied by 3, 9, 10. So we'll start by finding the inverse. So 1, 2, 1, minus 1, 2, minus 1, 3, 3, 1, 2. This method really develops your your attention to details. So 1 0 0 0 1 0 0 0 1. And okay, I'm gonna start by subtracting. Doesn't really matter what I do. I'm gonna do 2 minus 1. So sorry, 3 minus 2. 3 minus 2, and that becomes 1, 2 minus 1, 0 minus 1, 1. While we're at it, should I do anything else? No. Minus 1, 3, 0, 1, 0. And then we go 1, 2, minus 1. Ooh. That is a problem. Wait a second. 1, 2, minus 1. I did not expect that. Sorry. That's just cruel. Okay, anyways, it still works. And then it's going to be 1, 0, 0. This matrix does not have an inverse, so you can't use this method. Why does it not have an inverse? Well, because if you subtract 3 minus 1, you get a 0, 0 line. So basically it means the determinant. So determinant of matrix A is 0. A is singular. A minus 1 does not exist. Not exist. Okay, that's a pity, but that means we can use a different method. And I think it's called the Gauss method, just without the Jordan bit. So we can write down the same matrix, 1, 2, minus 1. And then this is called the expanded matrix of the system. Extended matrix of the system, 3, 3, 1, 2. And we can transform. So we take the matrix and the column. So we do the same. We do this minus that. So we get 1, 2, minus 1. And then 10 minus 9 is 1. And then 2 minus 1, 3, 9. 1, 2, minus 1, 3. And then we get subtract. Then we do 3 minus 1. And we get 0, 0, 0, minus 2. And 1, 2, minus 1, 3. 2 minus 1, 3, 9. And here, what we have to say. We have to say that the rank of matrix A is 2. Rank is the biggest 2 by 2 matrix you can extract. Sorry, it's the biggest square matrix you can extract from your matrix. The biggest non-singular matrix you can extract. The rank of A is 2. But the rank of A slash B, the extended matrix, is 3. How do I know it's 3? Well, I can see that this matrix is non-singular, whereas this matrix is singular. Singular. And this is non-singular. Singular. Now, I'm using very, very clever words like rank and rank over the extended matrix to understand that this equation has no solutions. Just look at the bottom line. The bottom line means 0x plus 0y plus 0z must equal to -2, which is nonsense. I don't know how to spell nonsense. So, not possible. Not possible. Okay. No solutions. No solutions. Right. Now, let's look at the final question. Or rather, let's modify the question so it does have solutions, so we don't. So yeah, let's do another one. Let's do a system like this, but I did not expect it to have no solutions. Let's do a system like this, but this time I'm gonna do 12 here. Okay, so 1, 2, -1 slash 3, 2, -1, 3, 9, 3, 1, 2. So this is still a singular matrix, but singular matrix, that means that the inverse doesn't exist. So we can't use the Gauss-Jordan method, for example. So let's do the same. So go 3 minus 1. So we get 1, 2, minus 1. And then 12 minus 9, that's 3. We get 2 minus 1, 3, 9, 1, 2 minus 1, 3. And now we do 3 minus 1 again. Oh, sorry, 3 minus 2 we did here. 3 minus 2, and now we do 3 minus 1. And now 3 minus 1, obviously the bottom row becomes 0, 0, 0, slash 0, which is perfectly acceptable. 2 minus 1 because 0 is equal to 0. There's no contradictions there, but that means we can just get rid of the bottom row and just work with 2. So 1, 2, minus 1, 2, minus 1, 3, slash 3, 9. So now what we want to do here, we want to transform the matrix by adding and subtracting rows until we get a something that looks like an identity matrix at the start. And that means that we have 2 minus 1, so that's going to be 1, then minus 1, minus 3. Nope. Minus double, so we get 2 minus twice 1. So, yeah, that's 0. Yeah, why would we do that? The 0. Then minus 1, minus 4, minus 5. And then 3 minus plus 2, so 5, slash 9 minus 6, 3. And get 1, 2, minus 1, 3. And then we get divide the second row by minus 5, so we get 0, 1, minus 1, minus 3/5, and we get 1, 2, minus 1, 3. And now we subtract the second row twice from the first one. So we get 1, 0, 1, and then 3 plus 6/5. 3 plus 6/5, 15 plus 21, 21/5 minus 3/5, 0, 1, minus 1. So we've achieved our aim. We achieved our aim of getting the identity matrix here. And here we just rewrite it in the form. So x plus 1x plus 0y plus 1z equals 21/5. 0x plus 1y minus 1z equals minus 3/5. And from here, we can see that x can be written as minus z plus 21/5. Y can be written as z minus 3/5. And z is just z, so it's independent. We say z is any number. Z is any number. We sometimes refer to this as 1 degree of freedom. So this the solution has 1 degree of freedom, or 1 independent parameter. Independent parameter. To make things simpler, we sometimes use t. Yeah, so we just rewrite it like this, and we replace z with t. Just to t, t, t. And so the answer is minus minus t plus 21/5, t minus 3/5, and t. And some of you will notice that this is an equation of a straight line. If it's an equation of a straight line in 3D, and indeed we have 3 planes which intersect along a straight line. Finally, problem 7. Find for which values of the parameter p and q do the simultaneous equations have solutions. Find the solutions if they exist. Okay, so there are 2 possibilities. So if it has solutions, it has unique solution if determinant of matrix A is not 0. So that's first, case 1. Case 1. Unique solution. So we have the determinant of 2, 1, p, 3 is not equal to 0. So 6 minus p is not equal to 0. So if p is not 6, it has solutions. Okay, so if p is not 6, so let's find the solution. So we can say y is equal to minus 2x plus 5. So px plus minus 6x plus 15 equals q. So x is equal to q minus 15 divided by p minus 6. Okay, and y. And as you can see why p is not 6, because if p is 6, x is does not exist. And then and y is x times that, so it's minus 2 multiplied by q minus 15 divided by p minus 6 plus 5. So that is minus 2q plus 30 plus 5p minus 30 divided by p minus 6. So that is 5p minus 2q divided by p minus 6. So y is 5p minus 2q divided by p minus 6. So that is the solution if p is not 6. Now, case 2. Case 2 is determinant A is 0, and that case we already know that p is 6. So if p is 6, then we have to have a look at the equations. So we have 2x plus y equals 5, 6x plus 3y equals q. Now, if we divide the second equation by 3, we get 2x plus y is 5, and 2x plus y is q over 3. If you look at these equations, 2x plus y is 5, and 2x plus y is q over 3. So the left-hand sides are exactly the same, so the right-hand sides have to be exactly the same. That means q over 3 must equal to 5, so q is 15. So solutions only exist if q is 15, and that means 2x plus y is 5. So any point on this line is a solution. Any point on the line is a solution. And that means y, or you can say y, or you can also express that as x equals y, sorry, you can say x is x and y is minus 2x plus 5. Or you can write x equals t and y equals minus 2t plus 5, where t is any number. Any real number, of course. So yeah, that is the solution. Okay, I think I'll finish here. I hope this was useful in ways. I have done this webinar before, so you can have a look at my old webinars on the same topic. Although last year I didn't do a webinar on this topic, maybe the year before. So please have a look. All right. So, all right. All the best, and see you. Oh, when do I see you? I'll see you. Webinars, year 13. The next webinar is on the 30th. So 3 weeks time, 30th of October. All right. See you.